Okay, so the two main features of things we're going to talk about in chapter 13 are one's called the correlation coefficient, and then the other one we're going to deal with is called simple linear regression. And in both cases, we're looking at relationships between two variables. So we're going to walk you through a few formulas. It's pretty straightforward. You just have to follow the process, and hopefully this will be maybe one of the easier chapters that we're looking at. Okay, so the basic idea behind a correlation is what we're going to do is we're going to measure the relationship, notice, between two variables. And down below you can see how they've inserted a scatter plot where you've got an x-axis and a y-axis. And in one case you're looking for age versus profit by the auto group. And you notice this is basically just a basic scatter plot. So the basic idea would be to try to measure, is there any way we could actually quantify a relationship between the two variables? And the first thing we're going to look at is what's called the correlation coefficient. So like I said, the coefficient of correlation, the correlation coefficient, by definition, is a measure of the strength of a relationship between two variables. And the idea is that we're trying to make these things fit on a line. So we're trying to see, is there a linear relationship? And the range of values that we're going to come up with can range, I'm just going to highlight this part, anywhere from a -1 up to a +1. And of course, if something is close to -1, you're going to say it's very negative. And if it's close to a +1, you're going to say it's very positive. And of course, you could also get numbers that are in between -1 and +1. And you just have to look and see how close that number is to 0 to indicate the type of relationship. Now, down below, obviously, they've tried to, again, give you more visuals. Notice how you have one graph where you've got, it looks like a downward relationship or negative, and the other one which looks like it is a upward or a positive relationship. And again, so the number we're going to try to come up with is, once we have got the scatter plot, is to try to measure quantitatively what the relationship is. And this, the first calculation is called the coefficient of correlation. And notice that the symbol we're going to be using is letter R. And so like I mentioned earlier, typically if you get a value that's close to the -1, you're going to say very negative. If it's close to the +1, you're going to say very positive. And you could also get numbers closer to 0, which are either weak negative or weak positive, or possibly even no relationship at all. Okay, and here's the formula, and we just have to follow it through. It's right here. I'm going to go ahead and circle it. And notice it's got a couple summations. Summation of x minus x bar y times y minus y bar. So we're going to set up a couple columns. And then we'll look at the sample size. That's a factor in it. And then, of course, the standard deviation of x times the standard deviation of y. We're going to walk you through this, and then this is going to give you the correlation coefficient. And so we're going to be looking at this particular example, and we're trying to measure the relationship. It's right here, the relationship between the number of sales calls made in a month and the number of copiers sold that month. And so notice we've got sales calls as X. That's going to be the independent variable. And the copiers sold is Y. And of course, here's the data. So they've already basically given us the sample information, and they've already plotted it in a scatter plot. And just a rough draft looks like there is a positive relationship, and we're just going to try to see how positive this number is. And notice, just to kind of walk you through it, so again, what they did was they got the sample mean for X, which is right there, it's 96. The sample mean for Y bar is 45. And then notice you have all these columns. You have, and they put this in the vertical. So you got X, you've got Y. And so then here's your X minus X bar, Y minus Y bar. So the basic idea would be, if I just kind of showed you the X, so it'd be 96 minus 96 is 0. 40 minus 96 get you to -56, and so forth. So you have to take each of these numbers minus X bar, it goes in this column. You do the same thing with the Y column with a copier sold. So 41 minus 45 would be a -4, and so forth. So you do that for all of this column. You put that here. And then, of course, notice they set up another column where you multiply. So 0 times -4 is 0. -56 times a -4 is 224, and so forth. And so once you've done that, notice you have to total this column, which they get 6,672. That's going to be our numerator right up there. And then we just have to get the denominator, which is the sample size -1 multiplied by the standard deviation of x times the standard deviation of y. Now, we've actually already done these calculations in previous chapters, so I trust you can go back and review the actual formulas and how they came up with it. So the basic idea at that point is you just plug these into this denominator, and then that's going to give you your correlation coefficient. And then just to kind of wrap it up, here's the actual numbers they're using, just like I had mentioned previously. Here's the formula. And so notice the sample size was 15 minus 1. Here's your standard deviation of x times the standard deviation of y. And then here's going to be the correlation coefficient. Notice it's a pretty strong one because 0.865 is very close to 1. So you'd probably indicate that in this case, this is a very strong positive relationship. Now, I'm not going to actually test you on this formula, on this test statistic. We're doing that in the hypothesis chapters. So as long as you can get the correlation coefficient, that's as far as I'm going to take it with chapter 13 on this particular calculation. And then the next tool we're going to be using is called regression analysis. So while the correlation coefficient measures the strength and the direction, it does not look at the concept of independence and dependence. So in other words, it doesn't measure the cause and effect thing. The regression analysis will factor in cause and effect. And we're going to be looking at this equation, which this is your linear equation, where x is going to be the independent variable. And of course, y will be the dependent variable. Okay, so again, the cause and effect is what the linear regression is going to be doing. And so we're going to walk you through a couple more formulas on how to plug in the numbers for the line equation. So again, we have this assumption of a linear relationship. And in this case, we're going to look at between the size of a home measured in square foot and the cost to heat the home. Okay, and then we're going to figure out how does the cost vary relative to the size of the home. Okay, that'll be one example. In the other one, there'll be a study of an automobile fuel efficiency. We're going to assume a linear relationship between miles per gallon and the weight of the car, trying to measure how does fuel efficiency vary relative to the weight of the car. And as you can see, again, like I said before, the y is going to be the dependent variable, which is the variable you're trying to predict. X is the independent variable. You're going to put that into this equation to use that to predict y. So if you look back to the size of a home, basically the home size is going to be x. Okay, that'll be the independent variable. And of course, heating cost is the y variable because we're going to see how is it affected based on the size of the home. Okay. And of course, in terms of the car, looking at fuel efficiency, the weight of the car is going to be the independent variable. And the gas or the fuel efficiency, we're going to try to see if how much does it depend upon the weight. So that would be the letter y. That would be the dependent variable. Now, the method that we're going to be using from the textbook, obviously, is called the least squares method. And then we'll walk you through the equations and how to figure out the slope and the y-intercept. Okay, so in this example, we're looking at sales calls being the x variable and copiers sold being the y. So we're trying to see how well does sales calls predict how many copiers are going to be sold. And we're going to plug it into this equation. I still like to write y equals a plus bx. And in this case, we're going to try to figure out what is the expected number of calls copiers sold if there's going to be 20 calls made. So we'll come up with the numbers and then try to make a prediction using this equation. And of course, you can go back and refer to the previous slide, but they went ahead and calculated the correlation coefficient already. We already got that 0.865. And remember, that is going to be represented by the lowercase r. Now, we're going to be using this number in the next couple of equations to figure out our slope. And here's the equation up here. So going back to the y equals a plus bx, where b represents your slope, look at the equation, which is right there. I'm going to circle it. It's going to be your correlation coefficient multiplied by the standard deviation of y divided by the standard deviation of x. And in this case, they already got the data for you, so you just have to kind of follow the numbers. So notice it was 0.865, which was the correlation coefficient. They already got the standard deviation of y divided by the standard deviation of x, and they figured out that the slope was right around 0.2608. Now, once you've got this one, then you go to the second equation, and right here, this is how you're going to figure out the y-intercept. Is simply And the y-intercept is letter A, just to remind you there. It's going to be y bar minus the slope times x bar. And of course, down here, they've got the numbers plugged in for you to show you how they calculated it. And so y bar is 45. Here's your slope. Notice you plug that right there. X bar was 96. And then they determined that the y-intercept was right at 19.9632. So then I like to go ahead and write the equation one more time to say that the y-intercept is 19.9632 plus your slope, which is 0.2608 times x. So this equation can now be used as predictions. So if we're trying to predict 20 sales calls and how many copiers were sold, you'd simply plug 20 in for x and solve for y, and that's what they do right here. And so in this case, they get about 25. Now, the last thing I would like to calculate is called the coefficient of determination, and sometimes it's referred to as R squared, which is basically your correlation coefficient squared. And the idea is to try to measure how much of the variation of y is actually predicted by x. So how much of a factor does x really influence y? And the higher the better. The range goes from 0 to 1, and obviously the closer to 1 the better, which means that that x variable does provide a lot of variation in y. And the way I'm going to have you calculate it is you go back and you've got the calculation on the correlation coefficient. All you got to do is square that, and that's going to give you your number. So in the previous example, we had a correlation coefficient equal to 0.865. So if we did an R squared, in that case, you'd get 0.748. Again, it's 0.865 squared would give you that, which basically means that approximately 75% of the variation in Y, which is copiers sold, can be explained by the number of sales calls.